So our next speaker is actually the only speaker from Rutgers today. Doron is a leading mathematician in the field of experimental mathematics, and I think we're very lucky to have him speak for us here. I think things balance out. He's the only one not using the projector, but he's also filming the thing. I don't know. And I think that one of the reasons why we invited him to talk in this conference is because we think he has an interesting and different perspective on proof. So, Doron.
Okay, the real reason Pablo invited me is so you can make fun of my crazy and stupid but not radical opinions. Speaking of this, it's very nice to see Lara, my former colleague, and I have to tell a little anecdote. When I was at Rutgers many years ago, I moved from Temple University, and I naively volunteered to teach the introduction to proof, whatever it's called, the bridge, MES 300. And first it looked good, because it all was fun stuff. So then, after I already committed, I was told by Professor Sachs, the undergrad chair at the time, that I'm supposed to fail half of the people. This is the way to distinguish. And I hate to fail people, so I already felt uncomfortable about this. And it turned out that I hated this class. And I'm never ever going to teach Introduction to Proofs again. At the time, I still like proofs. My love of proofs also is declining, and I hope to things. And I'm a very low-tech person, and I only use chalk. But chalk could be used for writing, but chalk has another application. Chalk could be thrown at people who use a laptop or any other electronic devices, or even check their iPhone very, very discreetly. Even if you're ostensibly taking notes, I don't trust you, and you might go to YouTube or Google. So please don't do that. Your laptop, or who lives, that's fine too. So you have a choice. Yeah.
I have your book, A equals B, on my laptop. Is it okay if I refer to it?
No, not right now. I don't completely trust you. And part of the problem, before starting, I'd like to narrate a few anecdotes. So with Lara, so Lara at the time was doing very, very interesting research. By the way, it was a very, very big loss that Lara left us. And particularly crushed was the former chair, now the executive dean, Rick Fogg, and said, there's a very, very big loss. Lara is the best teacher we ever had, and it's the great researcher in math education. It's a big loss, but she claims that she has some family ties in England. So he was particularly crushed, and every best was crushed. But speaking of Lara, she was trying to use my students as guinea pigs. She wanted to do some survey about proof comprehension. And I reluctantly agreed, because I hate to have my students as guinea pigs. Whenever the pediatrician, when my kids were young, a long time ago, they asked me, do you want to do this experimental test? Don't worry, it doesn't cost you anything, it's not dangerous. I always refuse on principle. My kids are not going to be guinea pigs for any study, so same thing with students. But since Lara is so charming, I reluctantly agreed. But then, at the time I had a grad student, Trevor Bass, a very, very smart student. Unfortunately, he decided not to go to do a PhD, but he was very qualified. And he took the math education class, grad class, that Lara took. Lara was teaching, and he loved it. And he told me how much fun it is. And part of it, they took the proofs the students gave from the last year's survey, and she taught them apart, and they made great fun, how funny, how stupid the students were. So once I realized that maybe next year when students will get the same fate, of course anonymously, we make fun of how stupid, how ridiculous the answers, the proofs are. I didn't tell you, Lara, I said in my mind, but if you remember, I declined last minute as an edge for a promise, so my students were still not used as guinea pigs. But the problem is not with the students, the problem is with the teachers, with the expectations. We expect them to know it's way over their heads. I have news for you. The people who get A's in math 300s, they don't have any more clue than about the proof comprehension than the people who get an F or a D. They have the appearance of understanding. You remember Alan Turing had the Turing test. And when a computer can simulate a human, well, you can fool somebody to believe it's a human. Same thing this, the A student is as good as passing the Turing test and faking understanding. Because understanding proof, even we don't have proofs. Because the notion of proof, the whole idea of proof, it goes back to stupid Euclid, way, way back. It's completely flawed, completely artificial. It's the base of a theology, even a polite word, theology. If you want to be polite, you say theology. If you really want to think, it's superstition. Astrology used to be a very respectable science until even 500 years ago. Kepler did believe in astrology, I'm sure, but now it's no longer taught in mathematics. So same thing with proofs. In 500 years, we think of proofs. Well, not quite as astrology, because the correctness is still there, but it's something completely useless, artificial. So, because I hate teaching proofs to undergrads, I love to teach grad students, but undergrad, because they usually don't get the point. Still, I wanted to teach last semester a number theory class. And then I looked at the textbook, and I almost, well, one of the adjectives, many adjectives was disgusting. I was disgusted by this proof. I opened a random thing. For poor undergrads, they have no clues about proofs, or they have hardly any clues. And remember, it's a 21st century. It's not the 20th century, the 21st century. The students are not as engaged as this. The same old boring styles that I grew up with. Theorem, lemma, corollary, elementary textbook! I wanted the name, but I'll take away the name. Elementary textbook supposed to be this. This is no fun. So I decided not to have a textbook and instead make my own notes, and in addition have links to Wikipedia. Wikipedia is much more fun! It is stupid! Obsolete, and this is probably one of the best textbooks for undergrads. We have to change things. Things have changed, and also proofs are no longer so important, and no offense to Euclid. Now we have the silicon master. Now we can have a new way of knowledge, and because human beings are so traditional, the inertia is so much. We still like our culture. We still find proof. In fact, my daughter is a math major, and I told her I don't like proof. She said, Dad, my proofs are so much fun. It's so much fun, like a puzzle. Also, my wife is a physicist. Said, I used to love proofs in geometry. So some people love proofs, and indeed, proofs could be fine, could be elegant. It's a nice art form, but their claim for truth, absolute truth, is not justified, because the proofs are usually made by humans, and they are subject to the whole doubts. There's still some sense that the Pythagorean theorem is false. There's no complete certainty in this life. So, proof is just a dogma, a religious dogma, and we have to get rid of this. But it's good news for educators. Instead of having proof and theorems and proof as the central feature concept in math education or in mathematical, it will be its algorithms. Algorithms. A good proof is a dead proof. Long live the algorithms. And many proofs can be phrased much more nicely, much more conveniently in terms of algorithms. And I'm going to illustrate. And that was my point in my number theory class that I just taught in the fall. You're welcome to go to my website. There's a link to the class, to my class notes. It's mainly algorithmic. I have I care a little bit of lip service to proofs and theorems because it's expected, but I try to minimize and stress the algorithmic aspects. And many times a proof is not a long-winded thing with just a verbiage. Can be much made shorter and encapsulated with an algorithm. So first let me comment about some previous talks today in this beautiful conference, a great, very interesting conference. It's really nice to go to conference, not in your narrow specialty. Math education is not math. Many, I'm embarrassed to say, many of my mathematical colleagues are very dismissive of mathematical education. And some of them are even very, very impolite. And I disagree with this. Mathematics education is not mathematics education. It's mathematics education. It's another completely different subject, different methodology, different expectations, and much more interesting than 98% of technical mathematics. For example, when I go to a typical math conference, I understand maybe 5%, to be generous, of the talks. Most mathematicians are completely dysfunctional. They just talk with a bum 50 minutes or half an hour. They talk whatever they learned in the last 10 years. They just repeat it in the speed of light, and they don't really care if anybody understood. There's many talking to themselves or many showing off, and they're afraid, in fact, that they be understood. Because the thing, if people can understand them, it means it's not that important or not that difficult. So maybe subconsciously they're trying to do this. So I was really enjoyed, I really learned a lot from methodology, and I learned some new words, the tool means things. But also I want to defend Poincaré and Attia and some other thing about simplicity. When they meant by a simple proof, they meant simple a posteriori. It's the kind of proof that you kick yourself after you see it, that you haven't done it. It's like a beautiful chess puzzle that you struggle very, very hard. But once you see the solution, you kick yourself, it's obvious a posteriori. So it's analogous to NP hard problem. It's easy to verify, but to come up with a priori. So probably that's what they meant by simplicity. So that's my defense of this. Also, I didn't like the proof of the sign. It was awful proof, very, it's an epitome of ugly mathematics. First, I don't like the word signature, it's too pretentious. I use sign. The sign of a permutation is that you have n people, different heights, and they then rearrange themselves. How many times you have a taller guy standing behind a shorter guy? That's called a number of inversions. So it really, if the number of inversions is even, it's +1. If the number of inversions is odd, it's -1. So if you have n people, you rearrange them again, then of course, either they got unrearranged, then you change the parity, or they got this. So either way, the parity of the number of inversions changes if you compose this and QD. So this was, I think, much better proof of this. And now I'm also very happy to see Hyman Bass, a former mathematician, former statements of mathematics, who very importantly became a professional math educator. He went into a conversion, religious conversion, and he realized that when he did his mathematics, even the best mathematics, at most, to be generous, 40 people could understand what he was doing or care about it. But doing education, math education, is much more important than doing yet another theorem that nobody cares about. So I'm very happy to see. Also, I owe Hyman very nice. Thanks to him, I have 2 papers and 1 opinion. I met him first when I was a young assistant professor at the Weizmann Institute, I think it was 1980, and he gave a beautiful talk about the so-called Jacobian conjecture, which I still remember today. And it inspired me to try to prove the Jacobian conjecture. Unfortunately, I failed to prove the Jacobian conjecture, although I did prove it once, but luckily I only told my wife, I didn't tell my dad. Then I found the mistake the next day. And it's still open. But I'm in good company. Yitang Zhang, who now famously almost proved the twin prime conjecture, he also, for his PhD, believed that he proved the common conjecture. Then his advisor, being nice, found a mistake, but he'd be able to make it a very special case and still got a PhD, but not enough to get a job. So, but luckily, it was a happy ending, as you know. about this. So that was the first slide. A month later, when I was at Temple in the mid-1990s, Hyman Best gave another beautiful talk, colloquium, about some combinatorial Zeller function. And this gave inspiration to one of my many opinions. Beware of colloquium wise guys. So in this case, I made fun of myself. When I saw all of a sudden the big Hyman Best, the fancy K-theories talk about stuff I know about, the matrix T-theorem, very down to earth combinatorics. I thought, what does he know? And I raised my hand. This follows immediately from the so-called matrix T-theorem, whatever it is. And then he was very polite, and maybe, but then I went back to it. It superficially looked very similar, but then it took us 2 years with my collaborator Dominic Fuata to have a combinatorial proof of this. So I thought I learned my lesson not to be a wise guy doing colloquium. So hopefully you was there. So now another history is one of my hobbies is family history. So I placed my ancestry. So here is me, and my mother's name was Ruth. Her father was Paul. His father was Solomon. And his father was Gershon. And his father was Solomon also. So he was named after him. This Solomon was named after him. And this Gershon, let's see, grandfather, great-grandfather had a brother. My great-great-great-uncle, Michael. He was born in a little village then he was Poznan, then he was part of Prussia. Maybe it was even already still Poland. Prussia became 1800. Anyway, later on, of course he was Jewish, I'm Jewish, so Michael was born Jewish, but then he became very famous, and he became the first Anglican bishop of Jerusalem. So this Jewish guy first decided that maybe Judaism is not what it's meant to be. And then he moved to England, and then he converted to Christianity, and then he rose through the ranks and became a bishop, and became the first Anglican bishop of Jerusalem. And when they asked him, why did he convert from Judaism to Christianity, he said, I studied the Talmud, and the Talmud is all full of petty, very petty minutiae. I want to have something with spirit, I have something with life, something with hope. So I discovered the New Testament is so much more fun, is so much more satisfying than just scribbling over these very, very petty things. Of course, if you're really into the Talmud, it's a game. If you're really into proofs, you can get into it. And very, very smart people I respect very much, they quibble about this very, very minute interpretation of the Talmud, and they have lots of fun, and they have their own pecking order, and it's a game like chess. But if you are not an insider, it can look very, very futile. So that's how I feel about traditional proofs, about traditional mathematics. So some of you of certain age may remember the hit song about 40 years ago of Paul Simon, when I remember all the crap I learned in high school, it's a wonder I can think it all. So my analogy is, when I remember all the crap I learned in grade school, it's a wonder I can think it all. All these stupid pedantic proofs that you made too. Because it's still today, experimental mathematics is still considered by most people not real mathematics. It's nice to make conjectures, but it's not knowledge. Real knowledge is a rigorous proof. So never mind about philosophy, I want to focus on the implications on how to change the teaching of mathematics and how to incorporate, even if you need proofs, to do it algorithmically whenever possible. So one of the things we torture about our students in the math transition is the square root of 2 is irrational. And I won't bore you with a traditional proof. With my students, 75% of the people, my students, never got it. They never got the point. Some of them could actually reproduce it faithfully, but that's being good copycats. But here is an algorithmic proof, a one-line algorithmic proof of the square root of 2 is irrational. Input! Every algorithm has input and output. Integers. A and B. Such that A square equals 2B square. Output. Integers. A bar and B. Such that A bar square equals equals to, B square. B square equals 2A. And in parentheses, A bar plus B is less than A plus B. And the proof, that's the beginning. That's how the beginning goes. Since A square equals 2B square, of course, A must be even, because it would be odd, then it won't be divided by 2. So you can write A as 2 and do the things, and QED. And so if the would have been, so it's a proof by reflection. So it's a fake algorithm. They do not exist. It's a hypothetical algorithm, but still an algorithm. If there would have been just to do integers, then you have a smaller pair, and the smallest pair of positive integers is 1, 1. And if you plug in 1, 1, 1 square is not 2 times 1 square. QED. So this is almost an algorithm. So it uses a little bit of logic, a little bit of proof of contradiction, but much less so than the very long-winded textbook proof. Suppose, assume that A and B with algorithms are relatively prime. If they are, divide them. Then you have this. Then you have A divided by 2. Then the contradiction, blah, blah. It's mental gymnastics. You can do it so much better. But still, this was not the original proof of the Greek. Famously, as I'm sure you know, the Pythagoreans were the big shock to their religious dogma that the square root of 2 is not a fraction, it's not a quotient of 2 integers. And allegedly, or possibly, Hippasus, who gave it away, was punished, either executed or excommunicated, which may be even worse, when he told everybody about this shock. But the proof of the Pythagoreans was not like this, as far as I know. Much better proof! More algorithmic, more geometrical with a diagram. Did I have a diagram? Somebody said diagrams are good. Yeah, I agree. Diagrams are good when they're relevant. So here is A. This is the closest to the Greek proof, I think. Here is the square A. And here is the square B. So suppose that you have two square, a bigger square, so it has to be a square, and a smaller square. So this is B square, and then the other B square, 2B square. So you have something common, and there's something left over. So this, so that's a terrible picture, but this is supposed to be twice this, if you have done it. QED. So in every scenario, we have two squares, A and B, and then you can form a smaller one. So if you do it with algebra, you really have a transformation. If A and B are such a pair, then if you look at it, this is A minus B. This is A minus B, and what's here is A minus B, A minus B. So it is B minus 2A. It's A minus M and B. So this is not the reduction one. If this is a solution to this quadratic equation, so this is the equation. But this is better. Because if you do the algebra, you get B minus 2A quantity square minus 2 A minus B quantity square equals, surprise, surprise, minus. So this is much better. You get the minus of this. In particular, you go down, down. So this is going down, prove a contradiction, but you can make it constructive. If you call this C and this D, you can go backwards. This is CD. And you have going up formula. This is much more informative and gives you much more than the stupid artificial textbook proof or square root of 2. So C comma D goes to C plus 2D, C plus D. And this beautiful, trivial but beautiful identity implies infinite many solutions, almost solutions. So the square root of 2 is not exactly irrational, but it's very close to it. You have what's called the affine-time approximation. And that's an algorithm. An algorithm is a recursive algorithm. So to introduce a sequence, an infinite sequence of solutions. So 1 comma 1 is almost a solution because 2 times 1 square minus 1 square is 1. But then if you do a table, it's an algorithm, a recursive algorithm to construct an infinite family of almost solutions to this. So it's this plus or minus 1. And it keeps alternating, so you get much more information from these things, and it's a beautiful, beautiful algorithm. So let me do, so CD, so 1, 1, it's 1. Then you do this transformation, 3, 2, 7, 5, 17, 12. So that's another proof. Now, Euclid was not all bad. He was bad by introducing the dogma, or the very conspicuous dogma of axiomatic method, because proof, but he was not all bad. I forgive him for all his sins. For a single beautiful algorithm, the Euclidean algorithm. And that's a terrific algorithm. And once again, the stupid book makes it a very, very long-winded presentation of this algorithm with proofs and things. So basically, it's almost trivial, but beautiful. The greatest common divisor of A and B is the recursion. You can program on a computer. Okay, if A is less than B, obviously, I don't need a warrant for this. The greatest common divisor of A and B is the greatest common divisor of B and A. Because if a certain number divides A and a certain number divides B, by the commutativity of the end relation in logic, the divisor of B divides D and by A. And the smallest is still true, so you have this. And if A is bigger than B, then you know that A minus B is positive. And that you can program in one line in your favorite computer. And you have an algorithm, not the most efficient algorithm, but still. So this means it exists and you can prove things. And of course you can do it with QR plus B, etc. And still it's much more fun to take the Euclidean algorithm and everything behind it. And using the Euclidean algorithms, you can get my favorite proof of the square root of 2 is irrational. You go to Maple. And you need 2 points to be a floating point. And then you do convert square root of 2 confrac. Maple has a command to convert any floating point number in decimal into continuous fraction. And before I know it, you get 1, 2, 2, 2, 2, 2, 2, 2, 2, 2. So this leads you to make a conjecture that even though Maple only gets up to whatever precision, 30, make a conjecture, it goes forever. So you make a conjecture, the square root of 2 of this. So this is an infinite, by the great algorithm, any finite rational number has a finite continuous fraction. It doesn't using the Euclidean algorithm. So since it's an infinite continuous fraction, it must be irrational. But still it's only a conjecture. But how do you prove it? So let's spell it out. It's called this x. You don't want to prove it. X is equal to 2. So if you spell it out, x is 1 plus 1 over 2 plus 1 over 2 plus 1 over 2. And you have set similarity. You call this y. And you have a set similarity. This y equals 2 plus 1 over the same thing. Because it goes forever. Infinity minus 1 is still infinity. So you have this beautiful thing. And then you go to Maple. Don't do it by hand. It's a waste of time. Don't waste your energy on doing things. You do solve. And you get to solution. Go to minus 1. Go to, and you can rule one of them out. And then you add QED. So this is an example of interacting with the computer algebra system and using algorithms in education. That's my approach for teaching. And also, I went to the joint math meetings, and I went to a beautiful, beautiful talk by historian of mathematics, an expert on Euler, William Dunham. And his proof, he gave a talk about Heron's famous formula. Very ancient formula, also beautiful. The statement is beautiful. None of the proofs. The statement can be beautiful and the proof can be ugly. Except for the proofs due to me coming up. So I was amused 15 minutes in excruciating detail. So let me remind you. Triangle with length, side length A, B, and C. And the area square is A plus B plus C times A plus B minus C times A plus C minus B times A, B plus C minus A over 16. That's the area square. And first, you get Heron's proof, 10 minutes of very elaborate diagrams. Then Euler's proof, 15 minutes. Then Euler claims it's better than Heron's. Then Newton's proof, 20 minutes. And then another amusing thing is somebody who believed, an amateur who may have been a crackpot by the name of Bernard Barney Oliver, sent him his own proof that allegedly was new, and maybe it was new, of Heron's formula. And it's funny story, first we saw it with some, not a crackpot, but some rank, obscure amateur. But later on it turned to be one of the greatest inventors, one of the founders of HP, very famous guy with all A's in geometry. And he got him to publish it in Math Teachers. In the collected works of this, you have Bernard Oliver's. He has another proof of Heron's. Better, much, much better than Newton's and Euler's. But not as good as mine and my computers. So a week ago I posted 2 one-line proofs of Heron's formula. And here goes. Of course it uses Maple. It's a one-line proof. So probably Newton knew about René Descartes, but he didn't care about it. He liked to do it the Euclidean way. But it's complete routine algebra, even for a human, but especially for a computer. So it's a one-line proof. If B A, let me explain. Eval B in Maple means Boolean evaluation. Eval B is true if this is true, and is false if this is false. So eval B, Dr. Z is crazy, is true. So eval B, and here goes. Expand. expands that expands an algebraic expression. And then subs. So you have some substitution. So one line maple code. Subs, open, brace, equals 1. B equals square root sqrt of x squared plus y squared. So it's one line, but I write big, so I have to go. Here in maple it's one line. You can go to my homepage. And then A is sqrt square root, open parenthesis, x minus 1 to the power 2 plus y squared, and close brace. So this is substitution, and here comes the expression. This expression, I'm too lazy to copy, minus y squared over y over 2 point square. So this expression, so copy and paste this here. And then equals 0. Parentheses, semicolon. And in 0 seconds, so not really 0 seconds, but a maple rounds up. It's probably 0.00001 seconds. So maple has a command called time. So I timed it. It was 0 seconds for maple, meaning finally 0. You got true! So poor Isaac, poor Leonard, poor Barney, and poor Hero, who worked maybe hours, maybe days on something in a complete triviality. And Newton could have done it too without paper. It would take maybe 10 minutes to do it. So let me explain. There's somebody called René Descartes, and he showed once and for all that geometry, all the things that all the school people and college students tortured and some people liked, but what people hated. And that's routine algebra. It's that high school algebra. So without going to the reality, A is 0, 0, B is 1, 0, and C is x comma y. X comma y as a variable, arbitrary thing. Then obviously A is 1. Sorry, B is 1. And A, by good old Pythagoras, the cheating not so much, is this. And also, by good old Pythagoras, is what is this? So this explains the subs here. Then the complete routine algebra. What Isaac Newton spent 2 days proving a new proof that 2 plus 3 equals 1 plus 4. It is the same epistemological stadio as this routine. This is an algorithm in arithmetic, in basic arithmetic. And this is basic high school algebra. And Newton knew it, but he didn't care because he loved doing it. Or maybe he knew it at some level. Or maybe he suspected René Descartes being French, I don't know. But okay, we forgive Newton. But nowadays. And another anecdote, how people love proofs, is so hard to do, is another beautiful theorem in geometry. Morley's theorem. There's an algorithm. The algorithm is built in any complete algebra system. It's called high school algebra. And for simple things, you do it by hand. But for more complicated things, and I have a package that my computer did of about 45 theorems in geometry. And my disciple, Matthew Russell, very, very happily now, he generated to 3 dimensions and also to hyperbolic and other fancy spherical and Minkowski geometry. Now he has a chance to be accepted in a semi-respectable genre, because that's Euclidean geometry. The best you can go in monthly. Even if you're a Lincoln or don't come me. So I was very, very amused. Beautiful theorem, once again, and the proofs are not so beautiful. Morley's theorem, as you know, if you have the bisectors, they meet at the point. But Morley, about 110 years ago, said the trisectors, and see where they meet. So you got an equilateral triangle. And one of the top 7 mathematicians of the 20th century, Alan Kohn, spent at least 2 days writing up a new proof of Morley's theorem. One of the top 20 mathematicians of the 20th century, John Conway, had another proof, beautiful proof, but still, he worked pretty hard to get this. And one of the top 100 mathematicians, my former colleague, Newman, he also had a proof. But Shalot Biachad, if you go to the homepage, you click on Morley, it's completely algebra. You just call this slope M, and then it does routine operations, and everything is just the same style as this. It takes 3 lines, there was 1 line, but still it's a routine algorithmic proof. So this, that's nice about humans. They still like these old-fashioned things. That's why I like humans still, because they're so cute. They still like these things, even though it's fairly obsolete. So it's okay to do it in your spare time. I'm sure Alan Kohn did it in his spare time. He didn't spend the French taxpayers' money doing it. It was a hobby, like people do. So I'm not blaming him. And also Don Conway probably. It was not a day job. He did for fun. Nothing to do with fun. But for the research we do, and for the teaching we do, we have to abandon this antiquated insistence on rigorous proof. Because already Gödel showed us, in addition to there exist undecidable things, there exist many, many, many statements whose statement is short, but his proof is very, very, very long. So, no offense to Andrew Wiles. If Andrew Wiles can prove something, it's not that deep, relative to humans, not bad for a human, but as far as the intrinsic knowledge up in the sky is still a triviality, because a human did it. Better than this, slightly, but not much better than this. Did it. So, if you want to have knowledge, we first have to go to algorithmic mathematics, experimental mathematics, and proofs are still okay, but not as a central feature of things. It's only as a byproduct whenever possible. And we should adopt this methodology, and I'm sure in 50 years it'll be commonplace. But hopefully I live in 50 years to tell you I told you so. But until then, I should be considered a semi-crackpot, or at best, an eccentric genius. Thank you. Okay, no, not questions, because we want to warm up. Behind me speaking in 10 minutes. Thank you.